Okay, so the recording is in progress. So let's start. So again, thank you for joining us today. The topic of the webinar today is how we model, how we perform thermal analysis, and also I'll focus this little bit on the thermal analysis where we have high temperature, like we have in fire, for instance, in the fire modeling. And then, with this, I will focus on the two analyses, actually, the thermal analysis, and then how to import the results from the thermal analysis into a stress analysis to calculate deflections, stresses in the structure, and maybe some collapse or failure. Let me a little bit highlight for those who are not so familiar with what we do. So we develop technology for modeling of advanced modeling of civil engineering structures with the emphasis of brittle materials, mainly reinforced concrete. Our motto is test your structure before you build it. So we like to see our software, which is the name of the software is ATENA. We like to see it as a virtual test of the structure before you actually construct it. And this slide kind of summarizes the types of problems that we usually deal with, starting from some laboratory experiments, maybe with random distribution of material properties, up to some large-scale structures like these containments at the bottom right. Let's say one of the main features of our software is the possibility to model reinforcement, as you see a little bit on this middle one. And with this, I will mention that also a little bit in my presentation. The focus there will be how we can actually also take into account the bond between concrete and behavior, and how this bond can be then affected by the high temperatures. So let me look at the workflow when we make thermal analysis, or let's say for the higher temperature modeling, this will be usually fire analysis. So for that, we are using two types of analysis. First, we make a thermal analysis. For that, we are using the transport module in ATENA. And then when we perform this thermal analysis, we can import this temperature data into a static analysis, or it can be also maybe creep analysis, but in the example I'll be showing today will be mainly static analysis. And here I want to emphasize that when we import temperatures, and we consider high temperatures, maybe reaching above 500 degrees up to maybe 1000 degrees. So we need to consider the effect, or the effect of temperature is basically in two ways. Once the temperature is inducing some strains, thermal strains, which expand our structure into certain areas, causing some strain gradients, and this may create deformations in our structure, maybe some cracking and so on. And the other effect of high temperature is that it degrades the material. So with this high temperature analysis, we need to make our material properties temperature dependent. So these are basically the two effects that we have in our static analysis. A little bit about the temperature modeling. We have these transport equations. Well, this is a little bit general because in ATENA, in the transport module, those who have looked at it, we can perform two types of transport analysis: transport of moisture and then the transport of temperature. So this will be the governing equations for the moisture transport, where the main parameter is the water content and relative humidity. They are actually related. And then we can have the moisture capacity. This is like the material property. And then we have the moisture flux. Analogical equations exist for the thermal analysis, for the heat transport. There, the main unknown is the temperature, and the material properties is the capacity, and we have the heat flux. And if you look at the fluxes, there we have these other two important material parameters, that is the moisture diffusivity and the heat conductivity. So if you think about these two basic parameters that we have, it is always the capacity and the diffusivity or conductivity. So, well, then we need to have a numerical solution. For that, we are using finite element method, 2D, 3D elements, and we have these two unknowns. These are the humidities and temperatures. And analogical quantities to forces, like we have in a static analysis. In thermal analysis, we have fluxes. That is basically the thermal transport or the humidity transport through a surface. Well, I am not going to talk in this in detail, but just basically to understand, we need to solve this kind of equations where this psi represents the unknowns, and we are marching in time. Always there is t plus delta t. So, and in this analysis, in this time marching scheme, we are always basically solving these equations where we calculate the increment of our unknowns, which are temperatures and moistures, based on this effective stiffness matrix K tilde, and this effective force, which is indicated by this J tilde. Well, so I'm not going to talk about much about these mathematical equations. I think everybody, if not doesn't know them, can easily maybe study them. Let's go now into more details that we need to address. So important thing for this thermal analysis is also the, well, maybe I'll skip this slide. This is important. For the thermal analysis, I told you that we have these two major properties, that's the conductivity and the heat capacity. And these properties, conductivity basically controls how fast the temperature or moisture propagates through our material, and capacity indicates the amount of heat energy or moisture that can be stored in a unit mass or volume of the material. So what is important, so normally, easily in most thermal analysis, we have these parameters as constant. But if we go to high temperature, that means we start to simulate fire analysis where we have temperatures up to 1000 degrees. We should take into account the fact that these parameters are not constant, and they change depending on the temperature. So as you can see here, the typical property of conductivity in time, for instance, for concrete, can have this kind of evolution. It is decreasing with increasing temperature, and capacity is pretty much constant, but depending on the water content in our material, we may experience this jump when we reach 100 degrees. This is the situation when the water vapor inside the material, or not only the water, but the moisture inside the material changes phase. That means from liquid to vapor. And this, of course, consumes energy, and it exhibits itself as a sudden increase in capacity of the material. So suddenly much more energy can be stored in the material. This additional energy that is stored in the material comes from the fact that this energy is necessary for the phase transition. So these are the nonlinear properties that we need to consider in the thermal analysis. And then I told you that we need to make the second step if we want to calculate the stresses. That means to perform stress analysis. And there we need to also consider the material dependence of our standard material parameters, which are typically Young's modulus. But in case of concrete, other parameters will be important. That is the compressive strength of concrete, tensile strength, fracture energy, which is the energy necessary to create a unit crack. WD, those of you who are familiar with ATENA, WD controls the softening in compression, and epsilon CP controls the amount of plastic strain when we reach compressive strength. So all these parameters should depend on the temperature. And you see some of the parameters decrease with temperature. Those are typically the strength parameters that you see on the top. But the parameters which control the ductility of the material, which is like the fracture energy, WD or epsilon CP, they actually increase. So the material, when it's being damaged by temperature, becomes more ductile. Okay, so this is some experimental results. So this is what I told you about. If we look at the compressive behavior in compression, we see that the material strength is decreasing, but at the same time, the ductility of the material is increasing. Similar behavior, although not so pronounced, is also can be observed in tension. These results are based on some experiments. For instance, these are experiments from Castillo and Durrani from 1990. Now about the boundary conditions. We need to understand that when we make thermal analysis, the boundary conditions is typically the temperature of the surrounding environment. So for that, we have a special condition. For fire analysis, it is this fire boundary condition. But even when there is no fire, when it is just a simple thermal analysis, typically we should use so-called convection coefficient. So we use actually similar boundary conditions where we apply some temperature of the surrounding environment, and then we define a convection coefficient, how this which controls the exchange of energy between the thermal energy between the environment and our concrete structure, or our structure, which doesn't have to be concrete, but in our cases now it will be concrete. And of course then always the exchange of temperature between the environment and the structure is by convection and radiation. Sometimes the radiation term is not so important, but in case of fire it may be important. So we have this additional coefficient controlling the emissivity, and then we have this max temperature which controls how our fire curve, in this case, what is the maximal temperature it is reaching. So we can have various fire curves in ATENA, and we can select them. There is also a possibility for a user curve. So this, I want to emphasize that in these transport problems, we typically do not define directly the temperature on the boundary, but we should always define the temperature of the environment, of the surrounding air, for instance, and then defining this convection coefficient. I am showing this on this example of fire boundary condition, but very similar condition. I will show that later on. We are using also for normal situation when the temperature is not so high as in the fire. And here are the windows for the definition of the material parameters. So I told you we can define this temperature dependency of the various material parameters like the E modulus, FT, tensile strength, compressive strength, and so on. So this normally there are some functions that are generated for typical situations, for instance, Eurocode. But if the user wants, you can directly modify it by hand. So the same dependency must be selected for the solid material and as well as for the reinforcement in case of reinforced concrete. What I want to mention also one more important feature that has been recently included in ATENA, and that is also the possibility to consider the dependency of the bond. In reinforced concrete, you understand that we have reinforcement there, which is an important part, providing the strength of the material in tension. And in ATENA, we can include a bond model. That means defining what is the strength between the reinforcement and the surrounding material. And now this bond can be temperature dependent also. So we have some bond law, for like you see on this graph on the top, which is, for instance, the FIB model code bond law, which depends on the concrete strength, type of reinforcement. And then we can define a degradation function, how this law degrades depending on the temperature. So basically, when you do that, it provides a scaling of this bond law, vertical scaling. Here I'm showing some example, and this example I will show you later on, and we will go through that in more detail. I'll show you actually in the software how the various parameters are defined. Here is just some animation. So this is, let's say, how this first thermal analysis look like. So we will subject the bottom surface of this, we can call it a small slab, to some fire condition. And you see how the temperature increase on the bottom surface, and this line represents the temperature increase on the top surface. And in this slab, we also have reinforcement, and here are just some results to understand this effect of the temperature on the bond. So we can introduce this dependency on, of course, also the reinforcement properties by itself, like the strength of the reinforcement. They also depend on the temperature. In addition, there is also a dependence of the bond properties. And maybe for you to understand a little bit how this bond is addressed in ATENA, so let me just summarize this so that we know what I'm talking about. So when we have a reinforcement in ATENA, so if you think this is some kind of beam and there is a reinforcement at the bottom, what happens when we in ATENA, when we start ATENA analysis, we always find intersections of this reinforcement, as you see on this figure on top, how this reinforcement intersects the individual finite elements. In this case, it is a brick 3D element. So when we are finding this intersection, we divide this reinforcement bar into small segments, and each segment is then embedded into the finite element. And when we do that, and then we consider, basically, we put some displacement constraints so that these displacement nodes, the displacement of these reinforcement nodes, are compatible with the surrounding displacements of the 3D element. This is basically a simple constraint equation saying that the displacement of this node is a linear combination of these surrounding displacements. But if you think about what this means, this assumption means basically a perfect connection. And we understand that in many cases we do not have perfect connection. We want to allow some slips, and in order to simulate that, we do by introducing additional degrees of freedom corresponding to a slip. And when we do that, always we can calculate what is the bond by just considering the difference between forces in the two neighboring bars. This gives us the bond strength. And when this bond, no, I'm sorry, bond stress, and when this bond stress is larger than bond strength given by our slip law, we can introduce slips. And there is a question from Todd: how do we define the convection emissivity coefficients? Is there a standard test method or literature available providing guidance on values that can be adopted based on concrete pipe class, etc.? Yes, this is a good question, and this is, well, I think the definition of these convection coefficients and emissivity, this is basically a whole area of research. But I think in the literature you can find these values. Even if you make a search on the internet, you can find for typical situations, because the what is the convection coefficient for a concrete wall, and it very much depends also whether there is wind and so on. So these coefficients can be defined. What we have in ATENA are some default values typical for instance, concrete. But if you need something special, you need to make some literature search. Okay, so this is what I was talking about. If I go back to this bond, I told you that we have these bars embedded into finite elements. We have this one node, which is on the intersection between two elements. And because we know the forces in the surrounding elements, this jump between them basically represents the bond stress. And when this bond stress violates our bond law, we introduce a slip. So this is, of course, a nonlinear equation, because based on the slip, we need to go back to this equation to calculate a new bond strength, compare it to recalculate the bond stress, depending on the difference between the forces of the two surrounding reinforcement bars. So this is, of course, an iterative process. So this is always solved for each reinforcement bar on which you activate the bond model iteratively. Okay, maybe here are some discrete slides about various dialogues. So I think I will close this presentation and let's look at the software itself, so we have some better understanding. Maybe I'll be switching back and forth a bit to the presentation later on. Okay, so we have this example, and for you to maybe play with it, it is available in ATENA software. If you start ATENA, I recommend you always to use this ATENA Center, which provides an interface to the various programs and tools. And if you click on the examples under this Git subdirectory temperature 3D, we have this, this is the VTEC 3D model. And in this VTEC 3D, we have this VTEC 3D fire, which exactly is the problem I am showing right now. So what we need always, we need to have two models. Once we, so this file name .gid, this represents the data file for Git, for the model preparation. And if for those of you who are familiar with ATENA, you know that when you go inside, there is a subdirectory ATENA calculations, where you will have all the results of the analysis once you run it. So for you to understand, so we first need to have this file and actually subdirectory where we define our transport model. This is for the thermal analysis. And then we need to create the static model, which is called here VTech 3D Stat. And there we will import into the static model. I will show you later how to exactly to do that. We will import the results from the fire analysis. And these data from the fire analysis are actually stored into some intermediary files. So that is this file and this file, yes. Bin represents the geometry, and THW, which is like temperature, humidity, water. So this actually contains the important data that we will later use in this static analysis. Here I want to mention this bin file, which contains the geometry. This is actually very useful, very important file. And I want to emphasize that because this allows us to use different models, different geometries, different meshing for the thermal analysis and for the stress analysis. And the program will then interpolate the results to the new mesh. So now I have opened this VTech 3D Fire. That's the file I'm showing you now. You see VTech 3D Fire. And let's then discuss a little bit the specific inputs for this thermal analysis. So I think I'm not going to talk about how to create the model in 3D in this 3D model in GAD. For that, you can use the other tutorials we have. But let's see what it is. Yes, this is some kind of a slab or half of a slab. Actually, it's a symmetrical quarter of a slab. Yes, of course, you can imagine it should go on the other way around. But for the simplicity to reduce the model size, I use this quarter model. And let's see what kind of boundary conditions I have. Well, let's have a look at the loading history. And loading history is seen by this this little clock, which says interval solution. And in this interval solution, we define interval data. As you see in this case, we have four intervals in our model. And they are used to divide the analysis or the time of the analysis. So if we activate the first one, and let's look at the boundary conditions we have. So I click here. Well, we don't see it because it is solid. So let me switch to render normal. So what you see here is that we have these circles, they are monitors. And these little fires, they indicate that there is some fire condition at the bottom. So let's have a look at this fire condition a little bit. So we see it's a surface condition. So we can activate this button for the boundary conditions. And here it's a surface conditions, and we know it is a fire boundary for surface. So we can now describe the various options we have here. You see this is the typical input data for this dialog. So if I see what are the conditions defined here, I can open these entities, and you see I have 4 conditions here. Let me transfer them so that I can answer them more in the window. So we are using this nominal hydrocarbon curve, which is, let's say, a standard Eurocode curve for fire in tunnels. And I told you we have these parameters: convection, important parameter, and this emissivity coefficient. So these are the typical values used for fire analysis. This temperature max defines what is the highest temperature reached in the fire. And min is, let's say, the starting temperature. Yes? This would be, let's say, the temperature our structure has before all this, before the fire event will start. So this is, let's say, defined in the first interval. And if I go here, again, look at the interval history, you see that I have defined this fire loading into several intervals. First one, second one. So first one is a very initial short interval, starting from 0 to 5 minutes. That's because you see here how this modified hydrocarbon curve immediately increases. So there is a very sudden increase in the temperature in, let's say, half an hour to 1000 degrees. So we want to capture properly this sudden increase. So that's why I recommend not to use, of course, we could have used a single loading interval for the whole fire, but I recommend to divide it into several intervals so that we can have different time stepping. So I have in this first interval, you see, I have 200 steps for 5 minutes. Then in the second one, I have from 5 minutes to 3 hours. I have, let's say, 400 steps. For the third interval, which is from 3 to 5 hours, this is actually this basically suppression, the suppression situation when they extinguish the fire. And then we have one more condition, or one more interval, I'm sorry. And this is, let's say, after the fire. Yes. So we say for another 1 hour, 1 day, up to 1 day, 24 hours. We use 200 steps for that. And this is to simulate the fact that how, let's say, the fire or the structure will be cooled down back to this original temperature of 25 degrees in this case. So let's, yeah, and what I want to show now, if I activate this interval, let's look at the condition here, because now it is after the fire. So we should use different condition. So you see now I don't have anymore the fire condition, and I have this moisture temperature boundary. So this is the condition I want to also show to you. This is the typical condition which you would use in most thermal analysis. So in most thermal analysis, you just define the ambient temperature and you define the convection. Please do not get now confused by the fact that we have also humidity here. This is because I told you that this transport analysis can simulate at the same time the transport of temperature as well as humidity. But this webinar today is really focused only on thermal analysis. So we do not activate this moisture part at all, and we are just using this heat convection and radiation. So we have basically the transport of temperature by convection and radiation. And this convection part is controlled by this coefficient. And actually, that's not what we use here. This is the default settings. But if I show you what parameters we used, I open them by these entities, then select the one I want to investigate, and I say transfer. And it now shows me actually what has been applied. So this is what has been applied in this case. Please turn off the microphone. Somebody has the microphone on. Okay. All right. And also what I forgot to tell you, that if you look here in this interval data, in all the intervals that we are analyzing now, we have activated this fixed moisture dove. That means we are not solving the humidity transport in this analysis at all. So one last thing I should also show you is the definition of materials, just to understand. So for the case of materials, if we click this button with the little eye, it shows us the materials used. I'm sorry, this one. So in this case, it is very simple. We have only one material called My Transport. And then we can go here to materials, solid material. And here we can look at this My Transport material. So this My Transport material has a useful tool that we can generate the necessary properties. So if I go back to, if I switch to the I don't want to damage this parameter, but it is derived from the CC transport material. And just for you to understand how it works, depending on the type of analysis that you want to select. So for instance, if you just want to make some, for instance, concrete at temperature, you just click here, generate and update. And it prepares the necessary parts that you want to do. It only activates the temperature. Here are the typical parameters that you only need to define. You need to define the initial temperature of your material, and that's it. So basically, only these two parameters are basic parameters, or these two parameters, K and C, are the basic parameters that are necessary for thermal analysis. In this case, we want to simulate concrete at high temperature. So we selected concrete at high temperature, type of conductivity, whether lower or upper limit, and we generate the material. And then you see it prepares the necessary dialogues here, which are a little bit more complicated. Again, we are only modeling temperature, so activate temperature is only selected. We again define these basic parameters K and C. And then, well, we could have also these advanced parameters, but normally we don't need them. What is important is this temperature dependency. So it creates these functions for the K. You remember I told you about, that's the conductivity, which is reducing. Or we select this dependency of the capacity, thermal capacity, depending on the temperature. So we define these parts in our model. Which is important is the material properties and the boundary conditions. And the boundary conditions are typically this moisture, this temperature, convection, and emissivity moisture boundary condition. And then we need to always to define the history by this interval data. In this case, we have these 4 intervals. Initial interval with very short time steps to activate this increase of thermal gradient, and then a second interval, another 2 intervals for the fire. Second one is up to the peak. Third one is, let's say, extinguishing of the fire. So that means gradual reduction of the fire intensity. And then fourth interval is the remaining time. So with this, we can run the analysis, which for the sake of time, I have already calculated. So we just, of course, we need to create a mesh. Yes, if we generate the mesh, we need to define some meshing parameters. I'm not going to talk about that because this is, let's say, standard Git process. Well, here, maybe what I should mention, you notice that I have kind of a strange mesh because in my situation, it is symmetric in this Y direction. So there is no need to put more elements. So I think it's enough if I have one element through the, let's say, in the Y direction of the beam. But of course, I need a very fine mesh close to the heated surface. So I use this concentrate mesh option in the mesh structured lines, concentrate elements to have the gradation of the mesh towards the heated surface. And then by clicking this button, I start the analysis. I'm not going to do that because I have already completed the analysis here. And here you see the result. So what you see here, you see the propagation or the development of the temperature on this is the heated surface, and those are the monitors which go at each of these depths, at each of these nodes that we depending on my division or my finite element mesh. And this last red one is again the point on the upper surface. So you see, of course, how this the temperature on the heated surface goes almost up to 1100, but not fully, as you can see. This is this difference of this convection boundary condition. Then we have the suppression of the fire, and then we have this remaining interval up to 24 hours. You see this time interval on the horizontal axis is time in minutes. And on the vertical axis, I have temperature. What is also interesting to see here is if you look at these profiles of the temperature development, you see that around 100 degrees, when we have this change of phase, you'll see kind of a bump in the temperature profile. And which is basically by this change in the capacitance of the material. What I forgot to mention, important thing. So if I go back to my Git problem, it is important how we actually tell the program where to store the data. So if I go to this problem data menu, where we define the general parameters of the solution, under the option time and transport, we define the two files where we want our data to be stored. I'm sorry. Those are the data from the fire analysis. This THW contains the temperatures, and this bin contains the geometry so that I can import and extrapolate the data to my stress analysis. And if I go back to see where are these results. So if you see, remember, I performed this analysis called fire, and now I will use this 3D static bond, and here I have these two files that I'm using to exchange the data. So now let's look at the stress analysis. I see we are a little bit running out of time. Oh, there is a question. Muhammad is asking, is it possible to concrete and composite material analyze together? I mean, at the same element like a beam. I'm sorry, I don't understand. Maybe it will be clear once I show the data for the stress analysis. So now we have this. So what you need always to do is that you can now take the same geometry that you used for the thermal analysis. You have to store it under a different name, and you have to activate to another problem type. This time it is a static problem type. Before it was a transport. And once we have this, so what happens is what you can do, you take the input data, you take the data from the fire analysis, for the thermal analysis, copy to a different file name, and then you just hit this ATENA static. So basically you change from transport to static, and it will ask you whether you want to transform the data. And of course you want to transform it. Unfortunately, because the material parameters and boundary conditions in the static analysis are totally different. So all the definition of materials and boundary conditions will disappear, because the material parameters and the boundary conditions in the static analysis are different. So then you need to redefine them. But of course, important fact is that the geometry, the shape of the model, you can use from the thermal analysis. So in this case, we can see that we have the same geometry, but now, of course, the loading history and boundary conditions will be different. So, so before that, also let's go to this problem data menu. And there under transport, again, we need to say where we take the data. So here we define again the data files, two data files, which we can use to import now our temperature results and the geometry to this thermal analysis, to this stress analysis. And important is the units also. We need to say what units are used in or were used in the thermal analysis. So before in the thermal analysis, we use seconds. So that's why we select seconds here. And now I'm not going to talk about the boundary conditions, how we define that, because I think you are familiar with that. Let's just quickly see what kind of boundary conditions are here. So let's look at the intervals. In this case, we have 3 intervals. So let's explore the first interval. And we can see what are the boundary conditions. I switch to the normal. So what you see here, that we have kind of a symmetric condition here. So that means this side is fixed in the y direction. This side, we assume also a plane of symmetry here. So this face is fixed in the x direction. Then we have some loads acting on the top. And then, of course, I have some monitors. Also here we have a support. On this line is supported in vertical direction. So it is like a simply supported slab. And we are modeling as a quarter of the slab. And you see here there is some reinforcement now, yes? At the bottom, we have some reinforcing bars. And now let's see what kind of loading history we have. So we have first interval is the load. So we apply some loads to the structure. And then we have 2 intervals with the fire. And again, we divide it because at the beginning, I told you this intensity and the boundary, the gradient of the force is so high that we should, or it is better to divide this fire loading into 2 intervals. So first we have a short interval up to, let's say, 30 minutes with many steps, 300. And then we have a remaining interval up to 3 hours of fire in another 100 steps. And now it's important here that we define how we want to import the temperature. You remember we defined at the beginning the files where we take the temperature data, but important is this button where we say read transport data. And we have 2 options. Either we extract them at the interval beginning, or for each step, we always extract the time interval which we define by the zone. So we are saying now basically that we extract temperatures from this temperature data file from 0 to 30 seconds, and we will apply them gradually into the structure. And actually, when each step is selected, that means this time interval is divided into 300 steps, and we do that separately for each step. So for each step, always it takes out the temperature increment and applies it to the structure. And we want to apply it also to the reinforcement, so that's why this button is also activated. So for you to understand, we always have to think about the loading scenario. In our example that I'm showing now, the loading scenario is such that we first load by force, and then we say it's like a structure which is subjected to some loads, and suddenly fire occurs. So we want to find out what happens. Actually, somebody says that he put a question in the Q&A section. Okay. Let's see. So the question is from Hamsek. Can you simulate a thermal shock where the temperature immediately drop to from 1000 to 25? Should I force the sample to cool down very short period? Will this impact the strength differently to where you allow the sample to cool down for longer periods? Sure, we can simulate that. That means basically you would have one interval where you apply some temperature up to 1000 degrees, and then I would add another interval where suddenly on the surface I would force the temperature to be 25 degrees. Of course, you can also have some transition in between, but if you want it really sudden shock, you can do it immediately. And then, of course, the behavior will be, of course, transient, that somehow the structure will experience this shock and will slowly try to accommodate that. Well, and the second part of your question, will this impact the strength? Well, strictly speaking, it will not impact the strength because it will be reducing the temperature. So no more damage will occur just by the fact of the temperature. But of course, the fact that you introduce this gradient of thermal strains, this will introduce huge gradients of strain into your model. And these gradients may cause cracks. And these cracks will, of course, then reduce the strength of or the stiffness of your structure. So this can be simulated. Another question is by Lynn van Wendner. Does ATENA Cloud have all the same functions as in the software? Yes. ATENA Cloud has the full functionality as I'm showing here. Except that what I'm showing here is actually the latest version, 5.9.1. which is still not yet on the cloud, but the differences between this version and the previous versions are not big. But some things may be slightly different. This is, let's say, still a beta version, which we are now releasing, this 5.9.1, and this is not yet on the cloud. Okay, so now let's at least briefly look at the results. Which one is it here? So here I have already calculated some results, and yeah, let's see what we see here. So this is I have some monitors there. One monitor is monitoring the total temperature at the bottom, and then I have a monitor monitoring the deflection. So you see here at the beginning there is a sudden increase of deflection up to step 20. So if I go to this step, so this is at the end of this static loading, yes? I told you that we first load the structure. You see how the structure deforms, and the load is such that already, let's say, the structure is quite heavily loaded. You see that there are already some cracks. And then if I go back to this almost last step, so this is this initial jump, and then we start applying the fire, and you see the fire, of course, is causing expansion at the bottom surface, which is, of course, increasing the deflection. And you see now I'm plotting this graph as a function of the temperature at the bottom. So you see at some point suddenly the temperatures, the deflection starts to increase very much. Now it is already, let's say, more than 10 centimeters. The units here are meters. And then we can explore the various results that ATENA, let's say, provides us. Now, of course, it is a question how to evaluate them and how to understand what is happening. Actually, in this scenario, it is a little bit difficult. It is a little bit more difficult to evaluate and understand what is going on, because we keep our static load acting on the structure, and now we are applying the temperature. This means that at some point we may experience a collapse, which we kind of see. We see that suddenly the temperatures, the deflections are increasing very much. What I'm plotting now is the tensile strength. And you see now that the tensile strength is very much decreased. So the material is, the blue indicates less than 0.4. So the temperatures are, the material is very much degraded. So you can see that there is, all these blue lines indicate damage, almost fully damaged material. So although the structure still seems to be somehow surviving, but the deflections are very large, and you see almost the whole cross section or the depth of the concrete is damaged. So I think we are running out of time, and so this is, let's say, the idea behind this. Of course, we could go very deep into this, but I hope this provided you some information. Of course, if you have more questions, please do not hesitate to contact us by email. And now let me go back to the questions. There is a question from Ricardo. Is it possible to make thermal analysis on hollow core slabs? Yes, sure, this is possible. But of course, one needs to think about what should be the thermal condition inside these openings. But anyway, again, the same kind of condition with the convection heat exchange can be used there. It is just then question to define the temperature for the interior of these hollow cores, and what should be the proper convection coefficient. And Paula has a question. Could you explain how to pass the temperature results into the static model? Okay, so let me briefly summarize that. So what is most important is that when I am in the transport analysis, under this button global data, time and transport dialog, here you define the two files. In the bidden file, it will store the geometry. In the THW file, it will store the thermal data. So this is the only thing you need to do. And then all the results from the thermal analysis will be stored here. And then in the static analysis, again, under the same button, problem data, there is a button transport. We need to say import transport results. And apply in interval data. And we select the two, we define here again the names and the whole path to these two files. And we define also the units that were used in the thermal analysis. So this defines the location of the files, but does not apply them actually. This just defines where the files are, where the data should be taken from. The actual application happens in the interval data. When you define the interval data, you see in the first interval, which is the classical situation, this read transport is not activated. So that means in the first interval, I'm just loading by the forces. I don't need the temperature data, so it is deactivated. But in the second interval, where I want to apply the temperature, I activate read transport data. And now I define the interval that I want to take out from the transport data. These temperatures are taken out for this interval, which is from 0 to 30 seconds. And now I apply this increment of temperature in the whole model, but it is not applied at once because this would be a huge, especially in case of fire, this would be a huge huge shock for the structure, I apply them in 300 steps. This is controlled by this. So here I say how large interval of temperatures I apply, and with this number of steps, I define how gradually it is applied. There is also this option that either I do it, I'm sorry, at the interval beginning. This means it will extract this whole interval. So imagine this at some point, the temperature increases at one single point from 0 to maybe 1000 degrees. So this information is extracted, this 1000 degrees. And now because here it is defined 300, so I divide this 1000 to 300 steps, and they are gradually applied. The second option is that I do each step. This means that in this 30, this is, 30 minutes, yes? So in these 30 minutes, I divide it by 300. So this means one step is actually how much? Like 0.01 second. And I'm sorry, 0.01 minute would be, yes, 0.01 minute. And this means it extracts from the thermal data what happens at one point in this interval, 0.1 minute. And this temperature increment then is applied in each step. But it does it, the difference is that now it does it step by step, because this increment may be in the first step 10 degrees, but in the other step it may be 0 degrees or 20 degrees. So it better take this approach with each step better takes into account maybe some gradual buildup of temperature gradient. So I'm sorry, I hope this somehow explains a little bit, but this is the main approach it is being used. And it applies it in the whole model. If you, for instance, doesn't want in some part of the model, you don't want this temperature to be applied, you can deactivate it by defining the properties of the material so that they are not temperature dependent, or their thermal coefficient is 0. Then it will be applied, but because the thermal coefficient is 0, nothing will happen. Okay, I'm sorry. I have some, I need to drink some water. Anyway, we are over our time, but I think it was necessary to answer these questions. And of course, if there are more questions, please do not hesitate to contact us by email. One more question by Hamzeh. Can I have a transport analysis only to assess the thermal expansion? Well, sure. This means if you do not want to consider the fact that the material parameters will be damaged by temperature, and you only need to consider the thermal expansion, this approach is being used. That's how you use it, because this actually applies the temperatures, and depending on the thermal expansion, the material will deform. What I didn't say, yes, because there's another important part, is that in the material definition, if I go to material definition for my concrete, yes, this is a good thing. I am sorry I didn't mention that. There is important part that in addition to these parameters, and actually I told it in my presentation, we have activated this material prototype here, as you see, is with temperature dependent properties. If we do that, we have this additional dialog, and there we can define how, for instance, the Young's modulus depends on the temperature. But if we don't do that, if we don't activate this temperature dependent material, then the only thing that will affect is the thermal expansion. If you look at the normal material, I can show it here. If you look at normal material, This normal material has just these basic parameters, and only other parameter is the thermal expansion. And the thermal expansion, depending on the imported temperature, will cause some thermal strains in the model. And there will be no degradation of material properties. Jan Vesetsky is asking, are there any future plans to include damage of concrete itself, not just reduction of material parameters due to temperature, spalling of the outer layer? Or are there even plans to allow for coupled static transport analysis? Uh, by that, I guess you mean the simulation of spalling, basically. The fact that when there is a buildup of water vapor pressure in the concrete, it may cause some cracking. Because the spalling actually has two let's say reasons why it happens. One is the pressure, vapor pressure in the pores. But the other thing is the spalling is also the result of the pressure in the layer of concrete, which kind of causes kind of a buckling, if you think about it. And this, in addition to this vapor pressure, may cause explosive spalling of concrete. And actually, if you look at the results that I showed you, you actually see that even our model without this water pressure is actually exhibiting this spalling. You see how this first layer of concrete is being cracked away. That's the conclusion of this huge pressure here, which builds up here due to this expansion. So this spalling is actually somehow, and you even see that how these concretes are a little bit separating and trying to leave away. They have almost zero strength anyway. So this is somehow addressed in the current model as well. What is of course not addressed is the fact that this concrete can fly away in an explosive manner, and the fact that this buildup of water vapor pressure, so this is not considered in the model. And right now, to tell the truth, we do not have any plans to develop this further on. But let's say it is a little bit in the back of our mind to improve that, but there are no immediate real plans on that. And one more, Hamzeh, in addition to stresses, can you monitor the mass loss of material? Well, as I told you, we do not consider the fact that some part of concrete is flying away. So the mass loss cannot be calculated. However, as I told you, we can have a display of the damaged material. So here, for instance, you can see which material, these blue areas, are fully damaged. So what you can do, there is an option in this, let's say, value limit. You can, for instance, say, okay, I want to display only the parts of the structure which has a, let's say, strength between, let's say, 0 and maybe 0.4. And you can do apply. And in this way, you can, let's say, have an idea about the extent of the structure. And strictly speaking, you could maybe export and somehow determine the volume of these elements, which I'm not sure exactly how to do, but I think it would be possible to figure out. So, and this, let's say, these fully damaged areas may somehow indicate material which is really lost. So this is only what is possible right now. Okay, I think we should finish now. So thank you again, all of you, to participating and to your questions. And I am looking forward to seeing you at other webinars, or maybe seeing you at some ATENA some conference or exhibition where we are presented. So thank you again. I'm stopping the recording.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.